Here, I'm going to briefly introduce to you derivative. So the derivative of a function is the slope of the function at a given point, namely the slope of the tangent line to this functional curve at any given point. Okay, so this is exactly the same expression of the tangent line, and here we especially name this function that is derived from the original function as its derivative. So it comes from the original function and is a derivative. So here, to note a derivative, there are several expressions. One is simply add a prime. So fx or y is the original function. Then we add a prime to tell you now we're taking derivative of this function for once. And here, dy over dx, that looks like delta y over delta x, but here we are using d to tell you it is infinitesimal change, namely that delta x is super small. And also you can replace y with fx, so we have the expression in the bottom. So there are several rules of calculation of derivatives, but here I'm going to start with the key rule, which is the power rule. Okay, so now we are focusing on one single function first. So now let's look at the power rule. So the power rule is here fx equals to k times of x to the power of n, and its derivative is n times of k x to the power of n minus 1. Okay, so here, now I'd like to switch to my document camera to demonstrate to you the use of it, why I'm naming this as the most important, as the key rule. Okay, so here, this is the single function case. Namely, there is only one function. Okay, let's do the most fundamental power rule, which is fx, if fx equals to x to the power of n, then f prime x equal to n by x to the power of n minus 1. So it is the n here, previous the power, now we copy it down, and then for the exponent, we deduct 1. So this is why I call this the fundamental rule. Now let's look at one case. Say fx equal to 3 equal to 5. Okay, that's the case where this 5 is a constant, right? So that's application. Now let's look at the application of this power rule, or according to what I put on the slide, the power rule is k multiplied by x to the power of n, and then f prime x. Now we keep k here, and then n by, so the k, which I actually refer to as the constant multiplier, a constant that is multiplied to this function, right? We keep it unchanged, and then we apply the power rule to x to the power of n. And its derivative is, let's pull n down, let's keep x. Now for its power, we deduct 1. So now let's look at this constant case. For the constant case, it is actually 5 multiplied by 1. We agree with that, right? And that is 5 multiplied by x to the power of 0. Why do I need to write it in this form? Because here we see you need an x to do the derivative, to apply the power rule. And here, anything with a power of 0, as long as it's not 0 for sure, then its value is 1. And here, x to the power, x is a variable. It's not restricted to only one value, 0, right? So it's to the power of 0 case, then its value is 1. Okay, so now with this function written this way, we can apply the power rule. All right, so here its derivative, for its derivative, what we can do is we keep the constant multiplier. In this case, that's 5. We keep it down, and now we apply the power rule to this function x to the power of 0. What we do is we pull this n down, right? And here n takes the value of 0, and then by x, and then the power, the new power of the derivative is 0 minus 1. What is the value of this? Anything multiplied by 0, its value is 0. So here it actually tells you, and this applies to, say, fx equals to k. It can be written the same way, k to the power of equals to k by 1 equals to k by x to the power of 0, and then its derivative is the same, k by 0 x 0 to the power of 0 minus 1, which is 0. So here we have this conclusion, which is the constant function rule, right? For a function that is a constant, its derivative should be 0. Okay, so you see the application of this power rule. So that's one. Let's look at another one. Linear. Let's start with a very simple case. Say y equals to mx. What is the derivative of this? F prime x, which is y prime, equal to, now it is m multiplied by x to the power of 1, right? And then that's why we can omit this 1 by writing this as m by x. So now, then we just apply this power rule. In this case, k, which is the constant multiplier, is your m, right? And the n is 1. And then we keep x, and now we have 1 minus 1 as the exponential of the new derivative. So it's m by 1 by x to the power of 0. As we previously discussed, that takes the value of 1. So it's m by 1 by 1, which is m. Okay, now let's check with our previous understanding. So what is a function curve of a constant? That is a straight line which is horizontal to your x-axis, right? That means no matter how your x changes, your y doesn't change at all. And here, let's go back to the conceptual reading, interpretation of derivative. Derivative is the instantaneous change rate, right? For every point, the instantaneous, there is no change at all. It's still the same value of y. It's still 5 everywhere, right? In this case. Then the instantaneous change is nothing. That's why its derivative is nothing. All right? Or if you think about the tangent line should be parallel to this point, then it's still going to be a horizontal line, and the slope of that horizontal line equals to 0. So now let's go to the linear case. Linear case, y equals to mx. So we have this line here, right? Then at any place on this point, the instantaneous change rate is the same, right? That's why we say the m, which is the slope term, right, is constant. This slope doesn't change at all, right? That means at any point, we have a constant rate of change, which is m. That matches with our intuition here. Okay, so now let's go back to the previous slides for other practice questions. So here, what are the derivatives of the following? The answer is 0 for all, for this constant case, right? And then what's the derivative for those? As we know, the derivative is just the slope term, right? It is 4 for the first one, 10 for the second one, and 8 for the third one. Why does the constant added to that doesn't change the derivative at all? Because that constant doesn't, as we previously discussed, the constant doesn't affect your change rate at all, right? Now, let's look at this. Just take one example. Let's do one application. So fx equals to minus 2 x to the power of 3, f prime x equals to. Now we just apply to this. So if you ever get confused, what you can do is to write down this equation, the formula on the side, and then apply to this actual problem. Here, what you need to figure out is what is k in this case? The k is minus 2. What is n in this case? N is 3, right? Then we just, as we are deriving for this derivative, what we do is we just copy down, plug in those numbers, right? It's the same k, so minus 2 by n 3 by x to the power of n minus 1, which is 3 minus 1. So the result is minus 6 by x to the power of 2. Okay, so that is the calculation, the application of rules of derivative for single function case. There is only one function in this case, which is fx.